Good morning, lovely 13s. Right, buddies. Today is your lucky day as we're starting a brand new unit. I know that everyone's going to be so sad to leave the forces and friction unit behind because it was such an awesome unit. But that's the beautiful thing about mechanics, is that all of the units are beautiful units. So you get to learn something equally cool and exciting. So the title, my lovelies, is Moments. Cool. Now, what a moment is, my lovelies, is it's just measuring kind of how a force interacts with something at a distance. So the easiest way I think to think about it is this picture here, which I've got of the Simpsons there, and see how Homer is really heavy, and he's at the end of this like seesaw thing, or probably whatever you call that in England. I probably call it, yeah, anyway. He's at the end of this seesaw thing, and what it is he's got the end pushed all the way down, and his entire family can't lift him up on it. And the reason why is because, well, he's a lot heavier, and all of their weights at whatever distance they're at isn't enough to lift him up. Cool beans? You can make things balance with moments as well. Look at this guy who's holding this stick with a blob of something on the end of it on his finger, perfectly in balance. So even though his finger's not in the middle, it's got to be more toward the heavy thing in order for the same mass to be on either side, in order for there to be the same moment on either side. So yeah, that's essentially what it is. It's measuring a twisting force. Now, normally, engineers call it torque. I've always learned it as torque as well. And so with the way that I've learned it, it's this. It's torque, which is actually the Greek letter tau. So it's torque, and it's just equal to force times a distance. It could be Fs, because S is the same distance as in Suvat. You remember how S was a distance in Suvat. Or it can be Fd, which I think is how your book does it, which is actually maybe easier. Just a force times a distance. There's one really funny thing with it though. The distances have to be the shortest possible distance to the line of action of the force. So while it looks like a really simple equation, it's a little bit trickier than you think, but I'll go through all the examples today and give you tons and tons of time to practice. It's not as hard as the last unit, I don't think, so I think hopefully you'll enjoy it and be really good at it. Oh, just before I move on as well, I just thought this was awesome. I remember these have you ever seen one of these like drinking bird things? They're kind of designed so that the head and the bottom part of the body are almost like equal in mass, so you can tip them back and forth, and water moves up and down their neck, and it makes them dip in and out of the water like that. And anyway, I remember the Simpsons episode where they did that, and I thought it was really funny. Yeah. Anyway, you should watch that Simpsons episode. It's very good. Anyway, yeah, here we go. So let's try it. Boom. Here we go. Really quick, easy intro ones. It says this: find the moment of each of the forces about the point P. So you always need to say where you're taking your moment about, okay? It's the hinge is usually what that's called, or the pivot is usually what they call that when you're doing it. But let's just do it. Here, I'm going to show you really easy peasy. First things first, a moment is just going to be a force times a distance, just like as above, right? Now, here's the thing. Remember what I said about the force has to be the shortest possible distance away from the hinge, okay? So here we go. You ready? Moments in this case, or the torque, is equal to the force, which is going to be 6, and then the distance is the shortest possible distance to the line of action of the force. So if you look at it, right down to the force, that red line I've just drawn is the shortest distance, because if I drew it this way, for instance, that would be longer. If I drew it that way, it would be longer. See, any line that's not a perpendicular line is longer. See what I mean? So this question is simply, I know I'm making it sound like it's a big nightmare, but it's simply just 6 times 3. That's good for our first question. So 18. Now, it's not got its own special unit, so it's just going to take it's just going to take the units of each of its parts. So force is a newton, a distance is a meter. It's 18 Newton meters. Now, there's something cool about moments as well, and that is that they have a direction, okay? So the same as a force, they're a vector quantity, okay? So in a square bracket next to it, like that, we need to say which way it would turn. Well, if you imagine like putting your hand here on P and holding this like stick at P, and someone was pulling on it, like at this weird angle, like at 90 degrees, and they're pulling on it, which way would it turn? Well, I hope that you'd see it would turn around that way, right? If you're pulling on the stick, it would end up making a revolution that way, wouldn't it, at this particular moment? Well, that's anti-clockwise. Now, instead of writing anti-clockwise, which is a really big word, it's sufficient just to write that. Draw a little anti-clockwise, some circle-y thing with a gap in it. Boom, done. Cool beans? Not too hard yet, eh? Now, here we go again. Moments here again. Moment or torque, because they're the same. Your book calls it moments all the way through. Moments are for physicists and torques are for engineers, really. But yeah, torque, moment, whatever. Torque is going to be a force times a distance, okay? Well, for sure the force is 12, because we can read that right off the thing. But here's the thing. We need to take the shortest possible distance to the line of action of the force. Here's what I mean again by line of action of the force. Here's what it is. See this force, this red line that I've just drawn right there on top of the force? That's actually the line that's representing the force, right? Now the line of action actually continues infinitely in both directions off the arrow, okay? So anywhere on the arrow itself or on those dashed lines that I drew, what's the shortest possible way to get to the arrow from P? Well, is it 8? Would you go down this way? Would it be 8? Is that the shortest distance? Well, no, definitely not. It's not 8, is it? There's a way shorter way to get to the red line from P, and the shorter way is here. It's a perpendicular way of getting there. This, my buddies, is the D that we are after. This is D. So it's not very hard still, though. What's D then equal to? If you look at it, we've got a right angle triangle, right? And this is going to be its only opposite, so it's sine. So we're just going to get here 8 sine 35, skipping the step of writing sine 35 equals d over 8. Cool beans? So there was that extra worry to it. There's that one extra thing that you've got to keep alert to. So a little bit harder this time, but just bosh it in. It's no problem, really. Times 8 sine 35 equals 55.1. 55.1, and I'm going to go with Newton meters. And in which direction would it spin? Well, if you imagine, my buddies, that you're holding it like here, you're holding it here near P, near the perpendicular distance, which way would it go? Well, it would spin it around like that, right, buddies? So I'm going to erase that now because it's sloppy, but it's clockwise. So it's okay just to draw that. See what I mean? Cool! Moments legends, my buddies. Moments legends. Okay. If only it just stayed that easy. Doesn't quite, though. So, next bit. Let's have a look. Let's have a look, buddies. So, oh, this is good, this one. Okay. Oops. This diagram shows two forces acting on a lamina. Now, I betcha you've not heard that word before, unless you do physics. What a lamina is, my buddies, is it's just any flat 2D surface. So if I was to say, like, take a piece of paper, that would be a lamina because it is a 2D shape that is filled in, okay? So it's not like a wire, it includes the thing around it. So if you wanted to draw this, it's as though this is acting on a piece of paper. See what I mean? It's like it's on a piece of paper. But anyway, that's what a lamina is, okay? It might become a little bit important later, and it will be definitely important if you take it at uni. Cool beans? So anyway, they're both acting on a lamina, so they are attached essentially to the surface. This is like it's on a piece of paper. Now it says find the moment of each of the forces around about P, and then we'll also say B. What is the resultant moment? Okay, I'm gonna make it harder. Cool beans. Well, here we go. Let's bust out part A really quick, okay? Because I don't think this one's actually too bad. So if we're going to start off here... Oh, I don't want to use purple. What color shall we use? I'll use purple. Let's just live dangerously, my lovelies. Well, here we go. Tell me the moment that's going to be associated with this. Pause the video. Go. Okay, it shouldn't have been too bad. That shouldn't need much of a pause at all. It's just going to be the force, which is 5, times the shortest possible distance to the force, which is actually just 2 this time, right? So this moment here is going to be 10, and the direction of it is going to be clockwise, it looks like to me. I think clockwise. If you were to consider your hand holding this, it would pull it around this way like a clock. Now, here we go. This one here, what are we going to get for its resultant moment? Well, it's just force times the shortest distance, so it's 8, And the shortest distance, is it 2? Well, no, it isn't 2 actually, because the shortest distance is gonna be this one here, okay? It's gonna be the perpendicular distance. The shortest way to get to something is the perpendicular distance. So the distance that we're gonna go isn't gonna be 2, but rather it's gonna be 2 sine 50. Cool? Sine because it's opposite, skipping a step. So what do we got there? 8 times 2 sine 50. 8 times 2 sine 50 equals 12.3. So 12.3, oh, I forgot the units in the last one, Newton meters, and the direction that this one's going to go in, to me, I think it's going to go anti-clockwise. Do you? Good. It's sometimes hard, well, I know when you're a beginner, it's hard to know if it's going clockwise or anti-clockwise, but just imagine that your hand is like grasping this thing here, and that's your hand, okay? Well, which way does it feel like it's being spun? Well, it feels like it's going that way. Cool? That's how I'd suggest that you do it, my buddies. Cool. Now, I added in a part B for you as well. So that answers A, because it was just a boring question. What's the moment of each one? But for B, what's the resultant moment? Oh my gosh, guys. This is going to change your life. This is going to blow your mind. Are you ready? You can almost do a net force equation on it. I've got another balance equation for you. So it's just like forces. Define a direction to be positive. Because I already know what the forces are and I want my answer to be positive. I'm going to start off with this. Anti-clockwise is positive. And just jot that. Check it out, buddies. T net, the overall balance of forces, just like F net. I'm going to call that T1, T1, T2, T2. So now I've named them. Oh, here you go. Which one's going positive? Well, T2 is. Which one's going negative? Well, T1 is. Get me, buddies? Because I defined anti-clockwise to be positive, which means that this is the positive, this is the negative. So the net overall force of both of these bad boys happening at the same time is just 12.3 take 10, which is 2.3 Newton meters. And which way will it go? Well, I said anti-clockwise was positive, and I got a positive answer. Anti-clockwise. Okay, so there you go, buddies. I hope it's okay, and I hope it doesn't feel too foreign to you. It should feel kind of normal because of the forces unit that we've just finished. You're good at FNet, and see, even though everyone doesn't do FNet, even though like I'm the only one, see, I'm not crazy. You can do all of this stuff and all of the units. Every unit's got a balance equation, and so does every unit at university too. So everyone's mad who doesn't do FNet. FNet, TNet, it's all good. Boom. Please try these. The lesson's not over yet, though, okay? So I'm going to do another topic. Page 72, question 2, 3, 5, and 4 is a trick question. In order to get 4, just remember it's the shortest possible distance to the line of action of the force. So you'll have to draw the force really long so that you'll be able to see where the line of action is. Spend up to 10 minutes because the video has already been 13 minutes, and then you're going to come back to me. Go. Okay, and now you're back to me. So I hope that those questions went all right, and I hope you checked your answers in the back. Cool. Next subtopic, my lovelies, is something I already cheekily taught you, resultant moments. And because all of the creators of Simpsons and Futurama were all mathematicians and physicists, you get lots of neat physics jokes in there. So yeah, it's cool. This is Mars University, and look at, they've got Mars University balanced with the annex on that because this is closer to the pivot and that's further away, so it's imbalance. I know they sneak physics in all over the shop in these really cool TV shows. Cool. So guess what? This unit's telling you that there's a net torque equation, or the net moments equation. Oh, I should say as well, I don't know if I said already, using tau, using the Greek letter tau for torque, or for moments, that's not going to be in your textbook, okay? People use the letter M in your textbook because I don't know. I've never known a physicist to use M, but your textbooks all certainly use M. M for moments, capital M. The only trouble with that is capital letters are usually reserved for forces, so it's a bit funny, but that's okay. I'm going to use moments, or T, I mean tau. Okay, the diagram shows a set of forces acting on a light rod. Okay, it says the rod is light. That means, buddies, that it's not got a mass at all. That's what that actually means. Calculate the resultant moment about the point P. Okay, so if you look at the picture, my buddies, what we've got is we've got P here. Okay, It's as though P is the pivot that the whole thing is sitting on. So that's me drawing a triangle, or trying to show that it is like a pivot, okay? It's like, yeah, it's the point where the thing is balanced on. It's not actually going to be balanced in this case. Cool. Well, guess what, buddies? You know, I just said that there's that net moments equation. Well, why don't we do that? Which way do you think it's going to turn? I'll give you a hint. It makes no difference if you're right or wrong. Which way do you think it's going to turn? I'm going to go with it's going to go clockwise because the 5 Newton force is far away from P. So I'm going to go with it's going to go clockwise. So here we go. Clockwise, positive. Cool. And let's do it. Net moments equation. Net. Okay, well, which one's going to make it go clockwise? If you think of each one individually, we're thinking about here, well, this 5 newtons, it's certainly going to want to twist it clockwise, right? So let's do it. It is a force times a distance. 5, and the distance is 3. That is the shortest distance because they meet each other at right angles. Cool. Any other clockwise? Well, no, ooh, no, actually, because this one makes it twist this way, and the 3 makes it twist that way, so that's it. Moving on to the 4 newtons, then it's moving anti-clockwise, because it wants to go that way around. Okay, so here we go. It's 4 at a distance of 1. Cool. And then on to the 3. It's on the other side, so you'd think it'd be clockwise, but it isn't actually, 'cause it's on the other side of the pivot. It wants to make it go this way around too, which is anti-clockwise. So take away 3 times 1. So there you have it, my buddies. That's going to be the answer to our question. It's 15, take 4, take 3. So the net overall force is just going to be 11, 10, 9, 8, 8 Newton meters. I said I said that clockwise was positive, so it's going to be clockwise because it's come out positive. Oops, oh drat. Yeah, happy days? Still not too bad, is it? It's not as hard as the friction yet, but that's because you're so beast at knowing what the net torque stuff is and net equations, balance equations. You're good at that. Okay. Now, here's the thing, buddies. If you really want a challenge, and I want you to really have a challenge, this is the same question, but with awkward forces, okay? Remember, it's the shortest possible distance to the line of action of each force. Now, if you're feeling brave, go ahead and pause and try it on your own. If not, I'll go through it with you. It is hard. Okay, and so here we go. Let's see how you did. Or some of you may have tried it anyway. Here we go. First things first, we just have to have a punt. It doesn't make any difference if we get it right or wrong. Do you think it's going to go anti-clockwise or clockwise? Well, I'm going to go with anti-clockwise this time because I think the 6 is going to cancel out the 5 quite a lot. So I'm going to guess that it's going to go this way. Anti-clockwise is positive. Cool. So here we go. Net. Now, here's the thing, buddies. To start with, anti-clockwise, let's do the 4. The 4 is certainly anti-clockwise. So it's going to be 4. But the thing is the shortest possible distance to the line of action of the force, is it that 3? Is there a shorter way to get to this 4 line? Well, yeah, there's a shorter way, isn't there? The shorter way is this. Perpendicular. If you can get to it using a right angle, that's going to be the shortest possible distance to the line of action of the force. So actually, the distance to it this time, it's going to be this distance here, and that's going to be, this is still the hypotenuse, and this is opposite, so it's sine. It's going to be 3 sine 40. Are you cool that this is 3 sine 40? Because the distance is going to be 3 sine 40, and then the thing is 4, so that's perfect. Cool. Let's move on to the 6. Is the 6 going to be clockwise or anti-clockwise? Well, it's going to be clockwise as well, so it's a plus, because it's going to make it twist the same way around as this one did. And here we go with it. The force is 6, and what's the shortest possible distance to the 6? Well, they do go perpendicular, so it's going to be 3. Nice and easy one. Cool. Which means the only anti-clockwise one is the 5, so I'm going to take a minus on it. And the shortest possible distance to the line of action of the force, is it 3 plus 1 equals 4? No, you're right, it isn't, because there's a shorter distance. If you can get to it this way, you can hit it perpendicularly. Can you see that that's going to be a shorter distance than the 4? If ever you just can draw a line to it and make it go perpendicularly, that's the answer, okay? So the whole bottom's 4, it's opposite. This is going to be 4 sine 80. Get me? Because it's opposite, and 3 plus 1 is 4 on the hypotenuse. So it's 5 times 4 sine 80. And there you've got it, buddies. So whilst it is tougher, because we're using trig pretty swiftly, it's not super tough. And you were using trig swiftly when we did inclined planes as well. So I think you're good. 4 times 3 sine 40, sine 40, plus 18, take 5 times 4, sine 80. Okay, I got that as 6.01. 6.01 Newton meters. And it looked, oh, 0.2 actually, whoops. 6.02 Newton meters. And because it came out positive, it means that I guessed the right direction, which means it is anti-clockwise. Happy days, buddies. Is that cool? Did you get it? Okay, sick. Final one. It's supposed to be the hardest, but I don't know, because you guys are so good, it won't be super hard for you. And there you go. Mine maybe dodgily cut and paste. My little, yeah. Anyway, here we go. Find the resultant moment of these guys as well. I only wanted to do this question because I wanted you to really get what the line of action of a force was. Okay, so we're at P again. Okay, but this time it's on a lamina, which means that we're in two-dimensional space. Okay, so there's two things. This could be on a piece of paper, and someone's pulling my paper up and left. Okay, what's the overall force going to be? Let's do it. Oh, we got to define a direction to be positive first. I'm going to go with, let's go with this way, anti-clockwise positive, and see what happens. Okay, so the overall forces is going to be this then. Well, you're going to have the one that's a 3, so we can start on it. So if you check it out, is this the shortest possible distance to the line of action of the force? Well, yeah, because it meets it perpendicularly. So here we go. It's just going to be 3. And it's going to be at a distance of 1. Is it positive or negative? Is that, if I was to imagine grasping this part here, and that being pulled up on it, what would it feel like? Yeah, it'd go around that way, wouldn't it? It does go anti-clockwise, so it is the positive one. Cool. Same deal now on this guy here. So, what's the shortest distance to this force? Well, if you said it's the 2, you're right, okay? Because we're trying to find the shortest distance from the point P to that. It's there, buddies. So first things first is if you were to imagine grasping it there, so there's your hands on it, okay? If you were to imagine grasping it there, which way is your hand going to feel pulled? Well, that way round, isn't it? So it's anti-clockwise, it's take away. So this is just take away 4 times this is 5 times 2, 2 times 5, same deal, but 5 times 2 to make it so I don't confuse anyone. And here we go. That means the overall moment is just going to be 3 take 10, -7 Newton meters. Oh dear. Oh dear, -7. Oh dear, what on earth does that mean? Well, you know what it means, don't you? It means this. It means that actually our direction convention that we guessed was wrong. It's 7 Newton meters for sure, but it's not anti-clockwise. It's clockwise. See? It makes no difference which way you pick. It's just, yeah, you said it was anti-clockwise. It came out negative. That means it was clockwise. Happy days. Cool. So that's it for today, my buddies. Oops. All I want you to do is them now, okay? So you do that till the end of the period. Give me an extra 20 minutes at the end of the period as well to keep working, because at least 20 minutes, because this is taking the place of homework, okay? So that's it from me. See you later. Bye, buddies!